Hi, this is Lawrence. I'm going to discuss with you the memory management concepts for Symbian operating system. This report is a requirement for our advanced operating system subject on our MIT class. First, let's have a trivia. Did you know that on June 24, 1998, Symbian Limited was formed as a partnership between Nokia, Ericsson, Motorola, and Scion? The operating system was known before as Epoch, which means beginning of the era, which is later on renamed to Symbian operating system as a result of the partnership between the four companies. So the topic we're going to discuss is the memory management concepts. We have six: address space and process, chunks, heaps, structure of a heap, virtual machine model, shared memory between threads. We will discuss this one by one on the succeeding slides. Address space and process. Programs in Symbian platform consist of a number of processes, each of which contains one or more conceptually concurrent threads of execution. Each thread is at least one chunk of memory. So each user has its own private address space. User process cannot directly access memory areas in the address space of another process. There is a special process which called kernel process, which normally contains two threads, which are kernel server thread and null thread. For the kernel server thread, it is used to implement all kernel functions requiring allocation and deallocation on a kernel heap. Null thread, on the other hand, runs only when no other threads are running. Places the processor into idle mode to save power. Next concept is chunks. Chunks map RAM or memory mapped input-output devices into contiguous virtual addresses. Under chunks, we have three types: user chunks, shared chunks, and local and global chunks. Under user chunks, we have three: normal chunks, double-ended chunks, and disconnected chunks. For the normal chunks, these chunks have committed region consisting of a single contiguous range starting at the chunk's base address and a size that is a multiple of the MMU page size. Double-ended chunks. These chunks have committed region consisting of a single contiguous range starting at arbitrary lower and upper endpoints within the reserved region. And disconnected chunks. These chunks have committed region consisting of arbitrary set of MMU pages within the reserved region. Next type of chunks is a shared chunks. A shared chunk is a mechanism that allows a kernel side code to share memory buffer safely with user side code. So shared chunks can only be created and destroyed by device drivers. Device driver is a computer program that operates and controls a particular type of device that is attached to a computer. Shared chunk is reference counted. So as long as the reference is greater than 0, shared chunk still exists. However, once all the reference of the shared chunk have been closed, eventually the shared chunk would be destroyed. Lastly, shared chunks may appear at different addresses within the address space of different user process. Last type of chunks is local and global chunks. So here are some comparison. We have the local chunks and global chunks. For the local chunks, it's private, not to be shared, doesn't have a name. Private, because it is not intended for access by any other processes. Not to be shared because it cannot be mapped, it does not need to be shared. Since it cannot be mapped, it doesn't have a name. Which is the opposite of the global chunks because it is intended to be accessed by other process, that's a name, so it can be mapped. Next concept is heaps. The main thread of a process has a memory chunk that contains the thread's heap. A program's request for memory is allocated from this heap. The heap is a region in your computer's memory that is not managed automatically for you and is not as tightly managed by the CPU. It's more likely a free floating region of memory. Structure of a heap. A heap consists of two lists of cells: the list of allocated cells and the list of free cells. So here in the figure in the slide shows the allocated cell and the free cell. The one in the black is the allocated cell and the one in the white is the free cell. So it is called heap because it is a pile of memory space available to programmers to allocate and deallocate. So as mentioned earlier, it's not automatically managed and it's more like a free floating region of memory. So allocation and deallocation of heap should be observed because failing to do this will turn your program will have so-called memory leak. Next concept is the virtual machine model. The kernel provides a virtual machine environment to user processes where each process accesses its data in the same virtual address range. So we have here two diagrams. The left one is the diagram for user process 1, and then the right is the diagram for user process 2. So on the left side, it shows that user process 1 is running and can see all chunks in the clear boxes. These boxes with dark background, or this one, represents the chunk which are not visible to user 1 process. So in the next diagram, when user process 2 is running, the context switch remaps the user process 2 data to the data section, and user process 1 data is remapped to the home section. So our last concept is shared memory between threads. So basically this describes the shared memory between threads and how to avoid race conditions. So what is shared memory? Shared memory is a method of inter-process communication where a single chunk of memory is shared between two or more processes. A thread is a unit of execution within a process. Every time a process initializes, a primary thread is created. Key concepts to synchronize threads: mutexes, semaphores, locks. For mutexes are used to serialize access to a section of reentrant code that cannot be executed concurrently by more than one thread. Mutex can be used by threads across any number of processes. Semaphores. Semaphores restrict the number of simultaneous users of a shared resource up to a maximum number. Threads can request access, so meaning decrementing the semaphore, and can signal that they have finished using the resources, or incrementing the semaphore. Basically, semaphore is a generous mutex. It's more on splitting into identical resources. For example, in lieu of a single buffer, a 4 KB buffer can be split into 4 1 KB buffer, which is identical resources. So last key concept to synchronize thread is locks. Locks are used to synchronize data when threads in the kernel are in the kernel. In SMP, threads are executed in parallel, which means that if locks are not applied to the code, it could result in a race condition. Race condition could lead to system crashes and data corruptions. What is race condition? Race condition is an undesirable condition that occurs when a device or system attempts to perform one or more operations at the same time. So basically, these are the key items to consider for the memory management concepts for Symbian operating system. The following are the reference for this report. I hope you learned something in this short report. Thank you very much.